All right, so this lesson is about friction and the friction force and how force applied at an angle will affect the force of friction on an object. So as a review, we looked at friction in grade 11 physics. So friction, FF, is a force that opposes the motion between two surfaces that are in contact. So it is an external force, okay? And it opposes motion. So therefore, its direction is always opposite to the motion. So because it's always opposite to motion, we always consider friction, FF, is negative when we're dealing with our FNet statement. So there's two kinds of friction forces. The first kind is static friction, and the second kind is kinetic friction. So static friction means no motion, just like static equilibrium, okay, no motion. So it opposes the start of motion, okay? It exists between any two objects that are in contact. It has a maximum value, which means if F applied is greater than the force of static friction, the object will move. If F applied is less than or even equal to static friction, if it's at rest, the object will not move. That's very important. So when the applied force exceeds the maximum value, the object begins to move. And so static friction, we would give it the symbol F sub s for static friction. The second kind is kinetic friction. And so kinetic means motion. So really kinetic friction is the friction, or what we call sliding friction. So it's known as sliding friction. It acts between two objects that are in relative motion, and all things being equal, the kinetic friction will always be less than the static friction. So static friction is the maximum, kinetic friction is less, and you can see there the symbol for kinetic friction is F sub k. So how do we get the value of friction? Well, the amount of friction depends on two things. Number one, the force that pushes the surfaces together, and that's the normal force. So again, what typically will push an object into another surface is the force of gravity. And we learned in our grade 11 physics that the normal force is the reaction force, Newton's third law. Okay, so Fn would be the reaction force to weight pulling down. So if you have a table and you've got a crate on the table, all right, the weight pulls down, all right, and normal force pushes up, and there is no relative motion between the two objects. The amount of friction also depends on the nature of the surfaces that are in contact, and a very non-scientific term would be the stickiness factor. So we have a symbol or a value that will represent the stickiness factor, and that's called the coefficient of friction. Okay, it's the Greek symbol mu, and it is a constant that depends on the nature of the two surfaces that are in contact. So, force of static friction will be less than or equal to the coefficient of static friction multiplied by the normal force, and the force of kinetic friction would equal the coefficient of kinetic friction multiplied by the normal force. So those would be your equations, okay, for friction. And also, of course, remember, the normal force is a reaction force to weight. And if we don't know the weight, we know that it's equal to m times g. And on Earth, g would be equal to 9.8. So on Earth, g would be equal to 9.8 newtons per kilogram, or meters per second squared. Okay. Let's take a recap look at an example we would have done in grade 11. Okay, so we have a wooden crate of mass 75 kilograms, sits on a flat surface. The coefficient of static friction is 0.362. and the coefficient of kinetic friction is 0.143. So if the crate is pushed with a horizontal maximum force of 270 newtons, prove the crate will move. Okay, so to prove that it will move, again, if we look at a free body diagram, okay, we have to have this applied force, F applied, and we'll just say it's to the right, forward. And we've got static friction, okay, Fs, to the left. So our F net statement would equal negative Fs, because it's opposite to the motion, plus F applied. And so for the crate to move, it must be bigger than the static friction. So if we move static friction, okay, to the right, F applied must be greater than the force of static friction, which of course we can expand. F applied must be greater than mu s, that's the coefficient of static friction, times m times g, because we don't know what the normal force is. All right, so we know that the force applied is equal to 275 newtons, and we can find the coefficient, we can find the force of static friction. So I'll just multiply it over here. Fs would equal mu, which is 0.362. Make sure you use the proper one, don't use the kinetic friction. So 0.362 times the mass, 75 kilograms, times 9.8. All right. So we'll take 0.362 times 9.8 times 75. And you get 266.07. 266.07 newtons. So F applied is 275 newtons. It is greater than the static friction force, which is 266.07 newtons. So therefore, the crate will move. Okay. So now that we know it's going to move, as soon as it moves, okay, kinetic friction is going to take over. So part B, it says determine the acceleration of the crate if it is pushed with a constant force of 275 newtons. So that was the force that was being applied. So now we'll do another FDD. All right, we've got our F applied to the right, and we've got our force of kinetic friction to the left. So according to our F net statement, F net equals negative Fk. That is, of course, being opposite to motion, plus force applied. Okay. So we want to find the acceleration, and we do know from Newton's second law, F net equals the sum of forces, which also equals ma, Newton's second law. Terrible A, sorry. So we can replace ma, and so ma equals negative Fk plus F applied. And so, again, building our equation, we know m is 75 times acceleration equals the force of kinetic friction, which we'll calculate over here on the left, plus the applied force, which was 275 newtons. So Fk equals mu k times m times g. So again, we go back up and we grab the proper coefficient, which is 0.143 for kinetic friction. So 0.143 times 9.8 times 75 kilograms. So 0.143 times 75 kilograms times 9.8. And you get 105.105 newtons. So 105.105 newtons. So that over here would be negative 105.105 newtons. And we can solve for A. So now A will equal the sum. So we'll just take negative 105.105 and we'll add 275 for the applied force. And then we'll divide that by the 75 kilograms. and you get 2.265 meters per second squared. 2.265 meters per second squared, that's positive. And we'll say, well, we don't need to put the direction because we know it's positive. And we have just solved for the acceleration, and that was something we did in grade 11. So that should be a recap from grade 11 for horizontal force. Okay, so now that we know this thing is accelerating at 2.265 meters per second squared, we can do some kinematics. So determine the velocity, so that would be a v2, of the crate after it has moved a distance, delta d, of 4.50 meters. So of course, the safe assumption would be a v1 would be 0, starting from rest. And we know acceleration is positive 2.265 meters per second squared. And we want v2, so we will use kinematic equation number 5. 2a delta d equals v2 squared minus v1 squared. So the v1 squared is 0. So v2 will equal the square root of 2a delta d. So 2 times 2.265 times 4.50, and we'll get the final velocity of the object. So we'll take the square root of 2 times 2.265 times 4.50 meters, and you get 4.51. We'll take 4.515. 4.515, okay, meters per second, and take it to sig figs, so that would be 3 sig figs. Now we already did the rounding before, so that should be 4.51 meters per second would be the V2. Okay, so that recaps horizontal force with friction. Okay, that was from physics 30S. Moving on now, we will look at what happens when friction occurs at an angle. So if we look at our horizontal plane, X, there are two possibilities. A force can be applied below the horizontal, okay, or it can be applied above the horizontal. So this would be above the horizontal, ATH, or below the horizontal, BTH. So what will happen is that when a force is applied at an angle, there's going to be components. And so because this is always measured from the horizontal, we can kind of make a conclusion here that if we have our applied force above, so F, we'll have two components, Fx and Fy, and that's our theta. Okay, so if this is above the horizontal, then Fx will be F cos theta, and Fy will be F sine theta. So very important for Fy, okay, if it's above the horizontal, it's positive, it's going up. Whereas, if it's below the horizontal, I'll draw the picture here. Our force is below the horizontal. Okay, I'm not going to rewrite the Fx, it's the same. So there's F, there's theta, Fy. And this is below the horizontal. Fy would equal negative F sine theta. So two different things. And you think about it, if Fy is directed up, it's going to be pulling the object up, which is going to reduce the normal force because it's counteracting weight, which is always pointed down. Remember, Fg is always down. Whereas if you push down on an object at an angle, it's actually pushing it into the ground, and so that Fy is going to add to the Fg, which is going to make the normal force larger. So the impact on friction is as follows, and I'll do it in a different color. If F is above the horizontal, okay, the normal force will equal mg minus F sine theta. Okay? And if the force applied is below the horizontal, then Fn, the normal force, would equal mg plus F sine theta. And again, it's due to the direction. Okay, if it's below the horizontal, the Fy is adding to weight, which means the normal force has to be larger. Whereas if it's above the horizontal, then it's going to be subtracting from weight and therefore reducing the normal force. Okay, so I would make sure you have a good grasp of those equations. And we'll look at an example and see what happens here. So we have a force of 130 newtons applied at an angle of 39 degrees ATH, that's above the horizontal, to an object with a mass of 45 kilograms. The mu s is 0.385 and the mu k is 0.144. Will the object move? So we'll start with a free body diagram. And again, we'll just go to the right as being positive. So we have our F applied, like that, F applied. Now clearly, what's going to push the object forward is Fx. What's going to act against Fx is Fs, static friction, okay? And we have weight going down, Fg, and we have Fy going up, okay? So that is a bit of a busy free body diagram, but we'll work with this. So the first thing we're going to do is deal with the vertical components to figure out what friction is going to be. So we're going to find Fs first. And Fs, remember, is equal to mu s times normal force. And I'm not writing mg because normal force is going to be different because we have a y going up. So we have to find Fn first. Fn, remember, or above the horizontal means that we are going to take mg minus F sine theta. So we'll do that. So it's going to equal mg, so 45 times 9.8 minus F, which is 130 newtons, sine 39. So we'll get that. So we will take 45 times 9.8, and we will subtract 130 sine 39. And we get 359.188. So 359.188 newtons. That is the new Fn, which we can then now apply to static friction. So static friction is the coefficient 0.385 times 359.188. So we'll take that number in our calculator times 0.385, and we get 138.288. We'll round the 7 up. So 138.288. So 138.288 newtons. So what is pushing this object forward? Okay, is a force of 130 newtons. But that 130 newtons is at an angle. So what force is actually pushing forward? Okay, Fx pushes the object forward. Okay, so now to determine if it moves, Fx must be greater than static friction. So our static friction was 138.288 newtons. Okay, and we have to find Fx. So Fx will equal F cos theta, as per our formula up here, F cos theta. So 130 cos 39. And clearly it's not going to be enough because 130 is already less than 138. But we'll still do the calculation. So 130 cos 39 is 101.03. So 101.03, is that less than one, is that greater than 138.288? This is false. Therefore, object does not move. You have to push harder with more force. So hopefully that gives you an idea of how we apply the two-dimensional, okay, aspect of an applied force. So this question here is kind of irrelevant. What is the final velocity of the object after 8 seconds? The object does not move, okay, because Fx is not greater than Fs. So the Vf would equal 0 meters per second. You'd be pushing on that thing for 8 seconds and it wouldn't move. Now, if the force was bigger, then if Fx was bigger than the static friction, then you would go back, okay, and do part B and part C, okay, to find the acceleration of the crate or the object and then the velocity if it actually moves. But in this case, it doesn't move because Fs is bigger than Fx. So for homework, I would like you to work on dynamics worksheet number 1. The answers are provided, okay, in brackets, so you can check your work. And good luck.